All right, 5.3 will be the last section that we're doing this semester. It deals with the fundamental theorem of calculus. It's also called the definite integral, what we're going to be doing here. Your book has plenty of definite integral questions from 5.3 and forward. So I'll be doing some questions from different sections in future videos. They also actually had it prior to this as well. All right, so let's take a look at some of this notation. First of all, the first part is it looks confusing, but really all it's saying is, here, let's select this. So first of all, f of x needs to be continuous, our function at x. So if you notice there's f of t in this integral here, but f of x is continuous over some interval a to b. Remember, in an interval, a is a smaller value and b is the larger of the x values. And the function capital F of x is defined below. So capital F of x evaluates some function t from a to x. So it's going to be evaluated throughout the entire thing. So essentially, we're going to get f prime of x equals f of x. And really, that just means the derivative of 1 is, the derivative of f of x is capital F of x is f of x, and the antiderivative of lowercase f of x is capital F of x. So that it just means you're taking an integral. How we put this into practice, however, is the fundamental theorem of calculus part 2. First of all, let's take a look at some of this notation here. This a, so this is the lower part of the interval. And then the b will be the highest value. And this notation here you should recognize. So capital F of b means f, the antiderivative evaluated at b minus the antiderivative evaluated at a. And what this is really giving us is the area underneath the curve using the x value. So how much area we have underneath the curve with respect to the x-axis. If it's above the x-axis, so positive, then that will be a positive value, positive area. If it's below, then it's actually a negative area. And I know that area can't be a value, you can't get a negative number for area, but in this sort of instance, we can. And if we have like the same value, like here, let's do a couple examples here. So just make an example of a function that we know, say f of x equals x squared. That means, if we take the antiderivative of f of x, that's x squared dx, which is x cubed over 3 plus c. All right, so how we would do this using our fundamental theorem of calculus, if we were going from, say, 0 to 1, so find the area under the curve for the interval 0 to 1. We would have, this is what it would look like. And this, how we typically write this, so x cubed over 3. The c is kind of redundant, and you're going to see this in a minute, and I'm not going to use the c after this for these. All right, so this is how we evaluate it. Remember, we take the larger x value, and we evaluate it there first. So this is going to equal f at 1 minus f at 0. Let's see if I can move down a little bit. which equals our f of 1 is 1 cubed over 3 plus c, and our f of 0 is 0 cubed over 3 plus c. Well, notice we're going to have a plus c and a minus c. So that's really just 1/3, plus c minus c, which is 1/3. The c will always cancel itself out, so we don't need to add it at all. And I won't be doing it in the future. So let's draw this graph here just to see what's sort of happening. So this is x squared. X squared looks something like this. This is the point, 1, 1. And the area that we're trying to find is this area here from 0 to 1. So that area is 1/3. Now let's slightly change this. We're going to let f of x equal x squared minus 1. So we're just going to shift the graph down 1, and it's going to put us below the x-axis. But let's evaluate the same thing. Only we're going to evaluate x squared minus 1. So the integral of this is, again, x cubed over 3 for our first one, but the integral of -1 is just negative x. And again, I'm not worried about the c. It's going to go away. So this is kind of how we write it. So we can do it like this. If it's a product, we can just draw a line as opposed to using the bracket. But it's the entire capital F of x going to be evaluated at 1 and 0. So this is going to equal 1 cubed over 3 minus 1 minus 0 cubed over 3 minus 0, which again is going to be 0. So that's easy. So this is 1/3 minus 1, which is -2/3. So our area is negative. It's just telling us how much area is actually below the x-axis. And you can get things that will zero out. So for instance, let's take this graph. So let's just take f of x just equals x. And let's go from -1 to 1. So let's check the integral -1 to 1 of x dx. Well, integral of x is x squared over 2. And here we have 1 squared over 2 minus, I'll put these here so to illustrate, -1 quantity squared over 2. So this is 1/2 minus 1/2, which is 0. So what it's actually illustrating here, let me see if I can do this. It's giving me this area, which is positive, and this area, which is negative, and they're symmetrical about the origin. So I have one that's going to be the positive component of the other. So 1/2 on one side and 1/2 on the other.